Welcome everyone. What we're going to do is we're going to go over some calculations involving using a formula as a conversion factor as one of the steps when you're converting from grams to moles or even to particles. Okay? So there's going to be an extra step and the actual formula will become a conversion factor in that new step. Let's take a look at this example. It says determine the moles of oxygen in 1.7 moles of calcium carbonate. Now notice they want moles of oxygen. Okay? So look what we need to do. The given is that we have 1.7 moles of calcium carbonate. Now, focus on oxygen. If you look at the formula, there is for every 1 mole of calcium carbonate, you'll notice there are 3 moles of oxygen. Okay? If we were looking at the other guys, carbon or calcium, there would be 1 mole of calcium for every 1 mole of calcium carbonate. And there's 1 mole of carbon for every 1 mole of calcium carbonate. But in this problem, our focus is oxygen, and there are 3 moles of oxygen for every 1 mole of calcium carbonate. So we're going to use this as a conversion factor. And what you're going to do is you want to cancel this part. So we want to say that for every 1 mole of calcium carbonate, put that at the bottom, there are 3 moles of oxygen at the top. And then it becomes a very simple problem because all you got to do now is you multiply 1.7 times 3, obviously divided by 1, it's the same number. These cancel, and when you round to 2 significant digits, you get 5.1 moles of oxygen, which is the answer to the question given. And that's it. 5.1 moles of oxygen. Let's try another. So here we want the moles of oxygen in 1.4 moles of H2SO4. So focus again on oxygen. According to this formula, there are 4 moles of oxygen in this formula for every 1 mole of H2SO4. Okay? So that's the conversion factor. Again, we're focusing on hydrogen. Now on oxygen. The given is 1.4 moles of H2SO4. So if we use this conversion factor, we want to get rid of H2SO4. So we want to put that at the bottom. For every 1 mole of H2SO4, there are 4 moles of oxygen. And then this is going to cancel. And the math is really simple. It'll be 1.4, okay, times 4 divided by 1, which is just 1.4 times 4. We'll round that to 2 significant digits, and you end up getting 5.6, and it'll be moles of oxygen. And that's it. You're done with this problem. It's a one-step problem. Okay? Now, let's take a look at something more complex. So here we have carvone. Carvone the formula is given. It is the main component of spearmint oil, has a pleasant aroma and mint flavor. It is added to chewing gum, liquors, soaps, and perfumes. We want to find what would be the mass of carbon in 55.4 grams of carvone. So here's what you got to do. In order to do that conversion that I just showed you, everything has to be in moles. This problem, there's an extra step. We're going to have to convert from grams to moles. And then once we're in moles, then we can use the conversion factor to get the carbon. Okay? So first we got to go from grams to moles. So in order to do that, we need to get the molar mass of carvone. Now carvone has 10 carbons. You got 14 hydrogens, and then there's that 1 oxygen. This guy is 12.01. These are all from the periodic table. Hydrogen is 1.01, and then oxygen is 16. So this becomes 120.1. This becomes 14.14. And then this becomes 16. And then what I'm going to do here is we're going to add these numbers to get the molar mass of carvone. So let me go ahead and do that, and we get 150.24 the unitary grams per mole. So if you recall, if we get the grams given, which is 55.4 grams, and we divide it by the molar mass of carbon, which is 150.24 grams per mole, and that means the G's will cancel, so we're going to be converting this to moles. So 55.4 divided by 150.24 gives us 0.36874, and I know there's more numbers. We're only going to need 3 significant digits anyways, but we converted it into moles. Now is when we're going to use the conversion factor. Focus on carbon, okay? We want the mass of carbon. So if you notice, there are 10 carbons for every 1 mole of carbon. So watch how I'm going to set this up. This is the number that we got here, the 0.36874. That's the moles of carbon. So I'm going to put here the formula, okay, like that. And now what I'm going to do is there are 10, okay, moles of carbon for every 1 mole of carbon. And what's going to happen is these are going to cancel, so you're going to basically multiply by 10, and I'll go ahead and write this down here, and I get 3.6874, and this will be moles of carbon now. Okay, now once we get to moles of carbon, we need to kind of go back. We need to go from moles of carbon to grams of carbon. So we're going to have to, if you recall, to go from moles back to grams, you multiply by the molar mass. In this case, it's carbon, so we'll just call it the atomic mass. The atomic mass of carbon is 12.01. So when you multiply by 12.01, that's going to convert moles of carbon into grams of carbon. Since this is the last step, I'll round to significant digits, which is 3, and I'm going to end up getting 44.3 grams of carbon, and that will be our answer. So we had to go from grams to moles of carbon. Then we use the conversion factor to go from carbon to carbon only, and then from moles of carbon back to grams of carbon. Let's try another one here. So here we want to find the mass of oxygen in a 5.8 gram sample of sodium bicarbonate. So again, we got to go from grams to moles. So let's find the molar mass of sodium bicarbonate. So let me go ahead and write the symbols here of these elements. There's 1 sodium, 1 hydrogen, 1 carbon, 3 oxygens. Sodium is 22.99 plus 1.01 times 12.01 times 16. So we'll go ahead and do the math here. This is 22.99. This stays as 1.01. And then we got 12.01 over here. And this is 48. So let's go ahead and add those numbers up. So 22.99 plus 1.01 plus 12.01 plus 48, we get a molar mass of 84.01. So if you get the grams of the sample of sodium bicarbonate and you divide it by the molar mass of sodium bicarbonate, which is grams per mole, we're going to go ahead and convert this to moles. So 5.8 divided by 84.01, we're going to get 0.0690. We'll round it to 4. We only need 2 significant digits. And that will be moles, and that will be of sodium carbonate. Now, we're focusing on oxygen. According to this formula, okay, for every 1 mole of sodium carbonate, you'll notice there are 3 moles of oxygen. So this will allow us to cancel, which basically all we got to do is multiply that by 3, and we're going to get 0.2071 0.18 moles of oxygen. But we don't want moles of oxygen. Okay, we want to convert from moles of oxygen to mass of oxygen because they want the grams. So the atomic mass of oxygen is 16. Okay, so you're going to multiply the moles by the molar mass, or atomic mass in this case, of oxygen, which is 16. We'll go ahead and round this to two significant figures, and you end up getting 3.3, and this will be grams of oxygen by itself, and that will be your final answer. Okay? All right, let's try one more. So again, here we want the mass of oxygen, and they tell us that we have 7.20 gram sample of aluminum sulfate. So what we're going to have to do is we're going to have to convert grams of aluminum sulfate into moles. So we need to find the molar mass of aluminum sulfate. We got 2 aluminums here. We have 3 sulfurs, if you look at the breakdown, okay? And then oxygen, we got 12. So we'll go to the periodic table. We'll use 26.98 for aluminum. Let me go ahead and fix that. So it's 26.98. We'll multiply that by 2 in a moment. This one is going to be 32.06, and your oxygen will be 16. And we're going to first multiply these before we add them. So 26.98 times 2 is 53.96, and then 32.06 times 3 for sulfur is 96.18, and then the 16 times the 12 oxygens, that's 192. Let's add these up so we can find the complete molar mass of aluminum sulfate, and when we do that, we get 342.14 grams per mole. So let's go ahead and get the grams given divided by the molar mass of aluminum sulfate. And what we're doing here is we're converting grams of aluminum sulfate into moles of aluminum sulfate. So we're going to go 7.20 grams divided by the molar mass, which is 342.14. We're going to end up getting 0.021044. There's more digits, but we just need 3 at the end. And this is moles of aluminum sulfate. Now, this problem wants the mass of oxygen. So let's use the conversion factor. If you look at the formula, there are 12 oxygens. Okay, so there's 12 moles of oxygen for every 1 mole of aluminum sulfate. So we're going to go ahead, all we got to do mathematically here is so that these units cancel out, okay, we just got to multiply by 12, and that will give us, and I'll write it up here, that'll give us 0.252528, and this will be now moles of oxygen only. But they want the mass of oxygen, so we're going to multiply by the atomic mass of oxygen, which is 16, and then we're going to round to 3 significant figures since this will be our last step, and you're going to end up getting 4.04, and it'll be grams of oxygen. So the new step in these problems is that whenever you see that they want an element within a compound, you have to do the extra step where you use that element as or you use the formula itself as a conversion factor. For instance, had we been looking for the mass of sulfur, the conversion factor would have been for every 3 moles of sulfur, there's 3 moles of sulfur for every 1 mole of aluminum sulfate. Had it been aluminum, we would have said that there are 2 moles of aluminum for every 1 mole of aluminum sulfate. In this particular problem, oxygen is the one that they were asking for. So the conversion factor was as follows. For every 12 moles of oxygen, that's how much there is in 1 mole of aluminum sulfate. So you have to read the question, pay attention if they are asking you for an element within the compound, and then use the formula of the compound to get the appropriate conversion factor.